Hi, welcome back to the Network Plus Certification video series. I'm Mike Redmond, Master Trainer, here to help guide you through your successful journey of becoming a Network Plus Certified Technician. We're going to walk through a wide variety of topics, starting with basic network concepts all the way through network management and security. In this segment, we're going to take a look at remote connectivity. I'll describe some of the WAN telephonic technologies such as SONET, compare last mile connections for connecting homes and businesses to the internet, and discuss and implement various remote access connection methods. So what is remote connectivity? Simply, it's connecting a local computer or network to a distant computer. Remote connections predate the internet, really. Private interconnections of private networks have been around for quite some time. The internet just made them a little easier and a lot less expensive. Today's interconnections use the internet, whereas before you would have to go the way of your own personal lease lines. And we're going to talk a little bit about that later. First, let's start with telephony. Well, telephony and beyond. So, as usual, the best place to start is the beginning. It all starts at Tier 1. Most of the high-speed internet backbones are still using old technologies, like SONET. Conventional telephone system technologies, like POTS or the plain old telephone service, have been around since the 70s and 80s. Believe it or not, it really wasn't until around the 1950s or 60s where you could even call across the country. Once long distance took hold, well, that pretty much made the internet possible. You used to have to ring a phone and a telephone operator would make a physical link so that you could talk to someone across the state or across the country. The fix for this was a lot of analog wires. However, we have a problem with analog. Analog signals lose their quality over long distances. So we had to find a more efficient way to get things done. Enter the multiplexer. It took a circuit and combined it with a few hundred other circuits into a single complex circuit on one wire. And then the demultiplexer on the other end of the connection split the individual connections back out. So in every central office, and they still exist, there's one or more of these exchanges. So let's look at the technology behind this. It starts with FDM, the frequency division multiplexing. It's your telephone frequency. It operates between 350 to 4,000 hertz. The multiplexer adds a frequency multiplier to each line. Each call is kept in its own unique frequency range. For long distance, a series of trunk lines is required. The operator had to connect those trunk lines. This essentially was circuit switching. Two phones physically on one circuit, the only option for analog long distance. So as I mentioned before, the analog was actually quite adequate from the 1930s to around the 1950s. However, once the society became more mobile, there was a need for better communication. This is where digital came in. A new digital system was needed for such a heavy load on the telephone lines. All these new remote connections were actually the precursor to the internet. Now, instead of multiplexers, we use digital repeaters. Even all the trunk lines are digital. So now your central office is converting analog voice into digital. And those central office users Well, that's the last mile. So let's talk a little bit about digital telephony. Technology used in later computer networks, this is where it all started. Digital packets were first adopted for telephony. The telephony cables, the frame types and speeds were truly the dawn of what we know now of the internet. However, it wasn't as complex. Most remote connections used only one type of cable and one type of frame, and you really only had one speed. But remember, all we are talking about at this point are telephone calls. So this new beginning, these are the digital signals called DS zeros. Analog sound converted into 8-bit chunks, and then those 8-bit chunks are transmitted at 64 kilobits a second. An analog call is converted into DS0 at your central office. So getting those digital signals to the right phone, well, it took another type of technology. This is where T1s and OC3s come in. However, we needed a method to switch across the network because they were no longer using multiplexers, so we're no longer circuit switching. This is where packet switching comes in. So before we get too much farther, you need to understand these different types of services. We break them down, starting with the copper carriers. These are T1 and T3s. The first digital trunk carriers were T carriers. A T1 is a high-speed digital network technology. A T1 line is specific shielded two-pair cabling. These terms are important for you to remember when executing the Network Plus exam. Next, we need to deal with the CSU-DSU, the Channel Service Unit, Digital Service Unit. There's one at the end of each T1 connection. The CSU-DSU connects the customer equipment to the central office. Here is what a T1 line looks like. So with the T1 signaling method, now we've moved to DS1s. By modern standards, it's relatively primitive frame. There is no addressing necessary on a point-to-point, remember. Your data is broken up into 25 pieces, totaling a total of 193 bits. These 25 pieces are placed into channels. There are 24 channels each with a single 8-bit DS0. This is transmitted 8,000 times per second, which is where we get the total rate or the total bandwidth equivalently for a T1 is 1.5 megabits. We call this time division multiplexing. Next is a T3 line. It's a dedicated telephone connection at 45 megabits per second. There are 672 individual DS0 channels, sometimes called DS3 lines. This is what your regional telephone companies and ISPs are using. There are similar but a little different standards when it comes to the European standard. An E1 is 2.048 megabits. It's carrying 32 channels at 64 kilobytes a second. The E1 and T1 can be interconnected. However, they will auto-negotiate between themselves. The E3 has 16 E1 lines and has a bandwidth of 34.368 megabytes per second. That's 512 channels at 64 kilobytes. Here's a look at the CSU-DSU ports on a Juniper router. The Network Plus examination expects you to know and understand the different carrier types, T1, T3, E1, and E2, how many channels each of them carry, and their maximum bandwidth speeds. Next, we move from the copper carriers to the fiber carriers. This is the beginning of SONET and SDH. Primarily, fiber optic carriers moved to a new international standard with these two names. It allowed the internet to expand worldwide. Starting with the OCs, or the optical carrier. These are what most of your medium or large size organizations' connections to the internet are. An OC1, for instance, has 51.8 megabits per second, whereas going all the way up to an OC768, well, now you're up to 39.8 gigabits per second. So how does SONET work? It starts with the STS, the synchronous transport signal. It's broken down into two parts, the STS payload and the STS overhead. An STS1 is 51.85 megabits per second on an OC1, whereas an STS3 is 155.52 megabits per second on an OC3 line. The Network Plus examination expects you to know and understand the different types of SONET and OCs that are available, as well as their maximum line speeds and their signal methods. Next, we'll talk about packet switching. The first generation of packet switching technology was X.25. This is the technology put in place when you need to connect multiple point-to-points, like multiple T1s, T3s, and OCs. We had to have a way to mesh all of these together, and packet switching was that answer. All packet switching protocols are functionally identical to a routable network protocol. There are two primary forms that dominate, which are frame relay and ATM. Frame relay is primarily what you're going to find with T-carrier lines. There's no guarantee of data integrity, however, and T-carrier lines really have a low error rate. That's often overlooked. In the United States, T1 lines all use frame relay. ATM, or asynchronous transfer modes, are designated for high-speed LANs. It's an extremely popular packet switching technology with WANs. Most SONET rings, as a matter of fact, are ATMs. And ATM, much like frame relay, works with frames at layer 2 rather than packets at layer 3. We'll get into more of that later. So ATM is broken into cells, short, fixed-length packets. Every cell with the same source and destination travels the same route. These cells are 53 bytes large. ATM is the most common amongst OC lines. Next, multi-protocol label switching, or MPLS. This is a router protocol for port selection. It addresses the issues ignored by ATM and frame relay. MPLS tells the router which port to use. It labels the data to use a specific desired port. This creates the MPLS VPN, a virtual tunnel. So MPLS has four major parts, starting with the label. It is used to determine how to move the data. Then the cost of service, or the COS. This is to be able to prioritize some packets over others. You'll have an S identifier. This is a single bit value that is set to 1 for the initial label. And then a TTL, or a time to live. This is the number of hops the label can make before it's eliminated. So again, MPLS is a routing protocol. However, where regular routers use quality of service on an individual basis, MPLS routers use their existing dynamic routing protocols to span an entire group of routers. To do this, you'll need to understand a few more parts, like LSRs and LERs. The LSR, the label switching router, looks for and forwards packets based on their MPLS label. The LER, or the label edge router, has the job of adding the MPLS labels to incoming packets. That then is passed off to the LDP, the Label Distribution Protocol. The LSRs and the LERs use LDPs to communicate dynamic information about their state, whether they're up or down, and the costs of those routes. Next, we have FECs. These are Forward Equivalence Class. It's a group of devices, usually they're computers, that tend to send packets to the same place, such as a single broadcast domain of computers connecting to a router. When an MPLS network comes online, the administrator will configure it initially with the routing information, the primary setting matrix to each of the routes. LSRs strip away the incoming labels and then add their own. This progresses until the packet exits out of the opposing LER. So how does this work in the real world? Well, telephony WANs connect LANs to the internet. They do that via the DMARC. Your ISP installs a CSU-DSU, which then connects to your router. The way they verify their connectivity is via a BERT. So now we've been given alternatives to the classic telephony WAN, starting with Ethernet over fiber. You'll find this in most big cities where fiber has been installed. It's extremely easy to set up and much faster than a T1 line. Also, we have DSL and cable. These are used only for internet connections. However, the downside is you cannot use your own equipment normally, and we have some last mile issues with DSL and cable. So let's talk about the last mile. It all starts with your telephone. You have two groups of telephone lines, dial-up lines and dedicated lines. There are several newer and different solutions available when it comes to this, whether it be dial-up, DSL, cable, satellite, fiber, or possibly even BPL. So with dial-up, you're using the PSTN, or the Public Switch Telephone Network. This is your POTS line, regular old phone. It's designed for analog sound data. Each individual cycle is clocked in what's identified as bauds, and that line has a particular baud rate. PSTN lines are 2400 baud. You'll use an RJ11 connector to connect to your plain old telephone line. I think you probably know that by now. Also, when using plain telephone lines, you don't have the CSU-DSU. You have what's identified as the NIU and the DMARC. The NIU is a small box that usually you'll see on the side of your house. DMARCs, it has the same premise, it serves the same function, it's just that's what they call the same connection for a business. So what we call a modem is actually two devices. It's a modem and a UART. When dealing with dial-up lines, you need some way to convert analog to digital and then back. We do that via the modem. The UART, or the Universal Asynchronous Receiver Transmitter, takes that 8-bit wide data and chunks it down to 1-bit wide data. This is your digital to analog for outgoing data, and then your analog to digital for incoming data. Understand, with your POTS line, you can rarely get faster than 33 kilobits per second. And because today's modern customer demands faster service, the solution is ISDN, or the Integrated Service Digital Network. It is capable of speeds up to 64 kilobits per second. So there are several different types of ISDN channels. You have B channels, D channels, and what's known as the BRI and PRI. The BRI takes 2 B channels and 1 D channel and puts it on a physical line. Each B channel sends 64 kilobits per second, giving you a combined rate of 128. The PRI, or the primary rate interface, is a full T1. It's carrying 23 B channels, which is how you get the 1.54 megabits per second. So the actual physical connection is very similar to the plain old telephone system. However, the ISDN wall socket is more similar to an RJ45 than an RJ11. This runs to your DMARC, to what's identified as the terminal adapter, or the TA. That is what connects to your computer. From there, it may possibly even include a hub for LAN connection. So to use and configure ISDN, you must be within 18,000 feet of a central office. That would be your phone company or ISP. Your ISP would provide you certain information to configure your connection, like a phone number and what's identified as a SPID, or the Service Profile ID. However, today, ISDN has widely been replaced by DSL and cable. In some locations, as a matter of fact, that's the only option. So with DSL, it is a fully digital line. It's provided by the telephone company and uses your standard RJ11 jack. However, DSL has the same limitation. You must be within 18,000 feet of a central switch. And the closer you are, the faster your connection will be. The farther away you are from the switch, the more degraded the connection will be. So as it applies to the Network Plus examination, these are the 3 most important DSL versions for you: symmetric DSL, asymmetric DSL, and very high bitrate DSL. With symmetric ASL, it's an equal upload and download speed. Theoretically, you should be able to get about 15 megabits per second. However, most ISPs only offer up to about 9. With asynchronous DSL, the upload and download speeds are different. Theoretically, download should be about 15 megabits per second, where upload should be about 1. However, most asynchronous DSL suppliers are going to throttle your speed back. You'll really notice this when it comes to your upload speeds. You'll usually max out right around 768 kilobits. Next is VDSL. It is the latest version of DSL. It hasn't really caught on in the United States very well. However, it does boast the same upload and download speeds, right around 100 megabits per second. The encoding method is how the increased speed is happening. You may be familiar with carriers like AT&T and Verizon, AT&T's UVerse and Verizon's Fios. Some of the main features of DSL are that you can use the same phone lines for both data and voice, simultaneously at that. However, again, you must be within 18,000 feet of a central office. DSLs use what's called a DSLAM. That's what's housed at the central office. It connects multiple customers to the internet. To install a DSL is pretty straightforward. You take your phone lines, which of course must be the standard phone line. It's going to filter out the DSL signal that comes across that line. To do this, you're going to need some special equipment, because DSL has three information channels. It has a high-speed downstream channel, a medium-speed duplex channel, as well as your POTS line or your phone line. So by connecting the filter to your phone line, it separates those DSL channels out from your telephone service. It'll connect via a regular RJ to the wall jack. However, you're going to need a Cat5e or better patch cable to go from the router to your NIC. First generation DSL used what's called a bridge connection. There's no authentication required. You just simply connect and you're on the internet. However, ISPs preferred the PPP over E, or the point-to-point over Ethernet. This requires a username and password, and you'll enter that into your home router. Next is cable modems. Originally offered as an added service from cable TV providers. The cable TV industry actually modified their entire infrastructure to be able to provide internet services. The cable modems today are very common. Most people will use them. It boasts theoretical speeds up to near 27 megabytes or better. However, in actuality, you probably will experience more like 10 megabits down and 1 megabit up, depending on your carrier. The installation of a cable modem, just like DSL, is very straightforward. The cable modem is connected to an incoming cable connection. Then you will take that cable connection and split it out. One will go to your TV and then the other to the cable modem itself. You'll connect to the PC NIC with an RJ45 and to the cable modem via a coax cable. Most modern cable providers have moved to a new standard, Data over Cable Service Interface Specification, or DOCSIS 3.0. This is the most recent and most current version because it adds primary support for IPv6. Next is satellite. For a lot of rural and remote locations, this is the only way available to get on the internet. And with satellite, you have two options. You have a one-way option, which is to download the signal from the satellite, and then you'll upload using, for instance, your telephone line. Or you'll have the option of a two-way connection where you will download and upload via the satellite. However, satellite is extremely slow, much slower than DSL or cable, but it's faster than a plain old telephone line. So it's a nice middle ground, and especially if that's the only option that you have. To connect to satellite broadband, it requires a satellite antenna. That antenna is going to connect to a satellite modem, and then the modem you'll connect to the NIC on your PC. And not to be outdone, many wireless carriers now offer internet service. Two basic types. Mobile data services, you know this primarily as your cellular network, whether it's GSM, CDMA, or LTE, or WiMAX. Not really a WAN solution. It is and has always been more of a MAN solution, or a metropolitan area network. It is only designed to cover for about 30 miles. LTE is the current standard from the cell phone providers these days. It is the main and primary competitor to WiMAX. It uses what's called high-speed packet access, or HPSA. All major wireless carriers support it, and extremely popular for portable internet access. Next, fiber. With fiber, you have two primary options, either fiber to the home or fiber to the premise. For instance, AT&T and UVerse offers fiber to the premise, whereas Fios offers fiber to the home. Unfortunately, it's not widely available yet. However, if you are lucky enough to be able to subscribe to a fiber connection, you should be able to enjoy speeds upwards of 100 megabits per second or better. Next, and it hasn't caught on quite yet, but it's coming, there's some issues with it, is broadband over power line. It's proposed to provide network over the existing power line infrastructure. This is called power line communications. It boasts the possibility of being able to service both voice and high-speed data. The problem really has been in the challenge of getting the electrical noise and interference off the line. Next, let's talk about remote access. So with remote access comes remote logon. There are many ways to do this, whether it be dialing up to the internet, having your own private dial-up, a VPN, a dedicated connection, or possibly a remote terminal or VoIP. We're going to take a look at each one of these in more detail. Starting with the dial-up to the internet. It's probably the oldest and the cheapest option available. To do this, you simply need a modem, an ISP provider, and a dial-up phone number, a username and password, some type of specified connection. Usually with dial-up, it's going to be PPP, and then your IP-specific information. Again, your ISP will provide you this. It'll usually be DHCP, which is only one step removed from a private dial-up. This connects remotely to a private network. It doesn't necessarily require the internet, it requires two systems. It requires a RAS, or a remote access server, and a remote access server's clients. To set up private dial-up, first you need to set up your RAS server. You'll need at least one modem that's capable of accepting incoming calls. Then identify your authentication method. Most common is PAP, CHAP, or 802.1x. Then on the other side, you need to configure your remote access client. It's pretty much identical to the dial-in to an internet service from an ISP. You'll obtain the information from the RAS server, however, this time, enter it into your client, and you're on. Next will be VPNs. VPNs connect to the networks via a tunnel. There are several types of VPNs. You can have an always-on type of remote connection, a dedicated private connection between two locations. This is where your T1 lines come in, or dedicated connections to the internet. This is where your DSL and your cable modems come in. So with cable modems, it poses a special kind of issues. The issues are that splitting causes signal degradation by half every time you split it. So splitting a cable with -3 dB gives you two cables with -6 dB. That is a huge loss when you're talking about an internet connection. Next, we'll talk about the remote terminals. There are a couple choices for you to choose from, whether it be a terminal emulator program, whether you're going to control computers remotely, or possibly the older, not wisely used Telnet text-based utilities. So again, just like you have options as to what type, you're going to have options as to what type of technologies. For instance, WinFrame from the Citrix Corporation, it requires a server and a client, whereas Microsoft Terminal Services only requires RDP to be active, or, which is included with every Mac OS and Linux, the BNC third-party terminal emulator. Next, we have VoIP, or Voice over IP. Two different types: real-time transport layer, or session-initiated protocol, or SIP. Real-time transport protocol is probably the most heavily adopted, whereas the competing standard SIP is capable of handling initiation, setup, delivery, and multicasting, whereas the real-time transfer protocol cannot. However, interestingly, both SIP and H.323 run on top of the real-time transport protocol. And then no discussion with VoIP would be complete without Skype. Now, Skype is completely different and incompatible with any other type of VoIP solution. It uses a peer-to-peer technology to connect calls. However, all the calls are encrypted, even though they're not encrypted through standard methods. And lastly, we have streaming media with RTSP. Streaming media with RTSP, the real-time streaming protocol, is what you get when you fire up your Windows Media Player or QuickTime Player. It runs again on top of RTP on TCP port 554. Well, there you have it. Pretty simple, right? I know, it can be a lot of information coming at you all at once, but don't worry, I'm here to guide you every step of the way. You can do this. Just remember, study hard, lots of practice questions, and you will succeed. You will become a Network Plus certified technician. I'll see you next time.